In this lesson, we're going to look at some of the properties of gases and describe the behavior of an ideal gas. Average kinetic energy increases with temperature. And when we're looking at the average kinetic energy, we're really looking at the average speed of the molecules. Because if I'm looking at particles of the same substance, their mass isn't going to change, and kinetic energy depends on both speed and mass. So these curves show the distribution of speeds for the same substance at 80 Kelvin and at 300 Kelvin. On the x-axis, we have the speed in meters per second, and on the y-axis, this is a measure of the number of particles at that particular speed. We have one curve at 80 Kelvin and another at 300 Kelvin. And these peaks give us the approximate average speed of the molecules. So what we see is that as the temperature increases, the average speed of a molecule also increases. Notice that it is the average that increases. There are still molecules at 300 Kelvin that are moving very slowly, and molecules at 80 Kelvin that are moving very rapidly. It's always a distribution of speeds, but we're worried about the average speed, which is increasing with temperature. Because the average speed increases, the average kinetic energy also increases. The next trend we want to look at is how speed correlates with the molar mass. And we see that the speed decreases with increasing molar mass. Again, we have speed on our x-axis. The y-axis is showing us the number of molecules. In looking at this graph, we need to recognize that all of these are happening at the same temperature. So we're only comparing the difference in molar mass with the average speed of the molecule. The graph shows us four curves, and the legend shows us the identity of each of those curves. Notice that helium, the bright blue line, is the smallest of the molecules, or smallest of the particles, and it has the highest average speed. Xenon, which is represented by the purple peak on the left, has the lowest average speed and also the highest mass. And what we see from this is that small molecules move faster and large molecules move slower. You should be able to determine the relative speeds based on the size of the molecule or on the temperature. You would never mix and match between different substances and at different temperatures. In this class, we are going to focus on ideal gases. The reason we look at ideal gases is because their behavior is very predictable. When we look at real gases, what we see is that things are not as predictable and more adjustments have to be made in calculations when predicting values. However, what we find is that most gases, under conditions that we use them in the lab or in the environment around us, behave like ideal gases. It's only under fairly extreme conditions that we have to account for the real gas behavior. In order to have an ideal gas, or the most ideal behavior, what we want are low pressures and high temperatures. At low pressure, we have fewer molecules per volume of the container, and so there are less incidences of collisions between those molecules, and there are less interactions between those particles. At high temperatures, we see molecules are moving very quickly, because we know that speed and temperature are correlated with one another. So as the molecules begin to move faster, they have less time to interact with one another. And it's interactions between molecules that lead to real gas behavior. So having low pressure, i.e. fewer molecules and molecules farther apart, and high temperature, molecules moving very rapidly, will lead us to the most ideal behavior of a gas.